In this lecture, let us talk about the FM signal generation using direct method. As I mentioned, the direct method can be based on either oscillators or relaxation oscillators. Recall this. So when I say oscillators, I mean resonant oscillators. I have a resonant circuit L and C. Relaxation oscillators, I will use R and C with the help of transistors. Therefore, the resonant oscillators or non-resonant oscillators are used to generate the FM signal by using a direct method. Okay, so in this lecture, I will discuss the case of the resonant oscillator. So how we can employ our resonant oscillator to get a frequency modulated signal. Okay, a resonant oscillator. So you take a transistor, it's an NPN transistor, then the emitter is connected between two inductors. Let me draw the inductor properly. Okay, and in parallel with you put a capacitor and connect like this, and this collector is connected to this, and this one is grounded C, and this one is L1, L2. You put a dot here, okay, and put one more dot also here. It indicates the coupling. So this is the schematic circuit diagram of such an oscillator. Okay, so this is the schematic diagram. That means I have shown a transistor, but I have not shown many of other components that the circuits will have. Okay, so for example, the transistor has to be biased as an amplifier, so it will have the biasing circuits. I have not shown any of that here. I am only looking at an AC model, okay, which is relevant for our discussion. So let's say this transistor with some gain, okay, so this transistor T has some gain in the output. There is a resonant circuit here, L1, L2 and LC, and the parallel LC circuit, and the resonant frequency F is equal to 1 over 2 pi times root of LC, where L is equal to two inductances, which is L1 plus L2 plus K times square root of L1 and L2, mutual coupling. The parallel LC circuit resonant frequency is this one, F is equal to 1 by 2 pi root of LC. And as we can see, there is a feedback mechanism. Okay, feedback mechanism in this circuit. Okay, these two inductors L1 and L2 are in series. They have mutual coupling shown by these dots. This dot indicates what? Mutual coupling between the two inductors. So if you take the output of the circuit as from, let's say, this point is A and this point is A dash, a portion of the output is also being fed again at the input through the coupling and through the coupling. So this L1 will act as a coupling. This guy will act as a coupling, and that will that gets amplified through the transistor. So you have this oscillating signal. So basically, as I mentioned, I'm not really going into a very detailed discussion of how an oscillator works here, but I'm just giving the flavor of that. But the important point is they have to have a feedback. You can see there is a feedback path here through the inductance L1, and that feedback builds up the circuit to produce an oscillation at a certain frequency. That frequency is given by this relation. Because this feedback occurs, that is the positive feedback occurs at the resonant frequency of the circuit, so whatever is the resonant frequency of the feedback circuit is really the frequency of oscillation. So other than that, I will not go into a detailed discussion. Okay, so remaining and all you can refer from your electronic circuits. So there are many kinds of oscillators. This particular one is called a Hartley oscillator. You have Hartley oscillator and Colpitt's oscillator and so on and so forth. Okay, replace these two inductance by two capacitance and this capacitor by inductance, then you'll get a Colpitt's oscillator. Okay, I am sure you will have a much more detailed discussion of the Hartley oscillator in your analog electronic course. And the oscillation frequency of this will be omega naught is equal to 1 over root of LC. And what is L? We said L1 plus L2. So in other oscillators, the feedback circuit will be in some other configuration. That will be the major difference from one oscillator to other oscillator. But here we have some, specific configuration. The feedback mechanisms are designed to be in different configuration. Okay, you cannot use the same feedback mechanism for for all other oscillators. It varies from configuration to configuration. Now let's assume here in the present discussion that such an oscillator is available to us. Okay, let's assume that we have an oscillator. Now the question that we have to address here is, can I use this oscillator as a source of FM generator? How can I use this oscillator to produce an frequency modulated signal? This is fine, working fine. Okay, from this oscillator you can get the carrier frequency FC, whichever you like it. Let's say 91.2 megahertz you can generate. That is not an issue. But what is our issue is, how can I convert this circuit in order that the output changes with respect to the message signal. So what features do I need to have in this circuit? Of course, your resonant frequency is 1 over root of LC. Either you make L as a function of your M of t, right? Because this is my resonant frequency oscillation, you make L as a function of amplitude of M of t, or you make C as a function of amplitude of M of t. Okay, therefore if you do that, then your 90% of the job will be over. Okay, therefore I need to modify this relation, omega naught is equal to 1 over root of LC. Okay, modify this relation or make this frequency omega naught of oscillation as voltage dependent. It depends on the M of t. How can I do that? How can I make it voltage dependent? Okay, make your omega naught as voltage dependent. Okay, I'm sure you can produce one or two answers. Okay, so at least one obvious answer is that you need a variable reactance or some kind of reactance, either through L or through C. Okay, so either inductor L or capacitor C should be made to depend on some applied voltage. It is as simple as that. That's it. Okay, somehow you change the N value depending on the voltage of the message signal, or you change the capacitor value in the circuit. Say I have the capacitor here, somehow change the capacitor or change any one inductor, which depends on the amplitude of the message signal. So you have to think of the most simple solution that comes out, and that is the obvious thing that comes to our mind. So if you want your oscillation which is frequency, which is depending on the voltage, basically the component which decides the oscillation frequency should be made to depend on voltage is the variable reactance or varactor diode. So you take a varactor diode, okay, you recover some kind of a variable reactance. So I'm not saying passively variable, okay, but actively variable. So this varactor diodes, PN junction diodes, these all are actively variable diodes, okay. So that is voltage dependent, so it has to have voltage dependent. Reactors or reactances which satisfy this property, I mean your C depends on the M of T or L depends on M of T. Here I am considering L, C, not L, okay. This property which have this are known by the name of varactors or variable reactors. So it has a varactor diode, varactors or variable reactors. Sometimes people call varicap also. So the varactors are variable reactors. Here voltage, it depends on the voltage dependence. It depends on the voltage. Most of the time it is very difficult to find naturally occurring voltage dependent inductors. So there is no inductors such that. But naturally we have a voltage dependent capacitor. Right. On the other hand, a voltage dependent capacitance is something that you can easily build using your semiconductor devices. Therefore, the varactors are simply known as varicap. Simply known as varicap. It is a variable capacitor. Varicap means what? Variable capacitor. Why does it is varying its capacitance? Because of the applied voltage. Voltage dependent capacitor. Okay, an example of variable capacitor or voltage dependent capacitor is like the junction capacitance of the PN junction diode. You take a PN material, there is a junction, and in this junction you have depletion capacitance and diffusion capacitance. Okay, so the junction capacitance of PN junction diode is an example. Particularly the reverse biased PN junctions, it gives the depletion region, and because of that you will get a depletion layer capacitance. In the reverse bias mode, you know that the PN junction has a depletion region. Recall from your devices. Depletion region. Because of the depletion region, you have depletion capacitance. It has depletion capacitance. In the this capacitance occurs in the reverse bias. If you forward bias FB, then you have something called a diffusion capacitance. Okay, in the reverse biased mode, you know that the PN junction has a depletion region, and across the depletion region we have a capacitors, and there is and this capacitor depends on the voltage, applied voltage. So the junction capacitance of PN junction is an example. This PN junction diodes, PN junction diodes which are specifically used to exploit this property. They are designed to give you a good variation of capacitance with voltage, are known as varactor diodes or varicaps. And the actual dependence of this capacitance on the applied voltage may not be exactly a linear relationship. Typically it is a non-linear relationship, right? So you got a capacitance, and that capacitance depends on the applied voltage, and the relationship between the capacitance available from the diode or from the device and the applied voltage are not in, doesn't have any linear relationship, these two guys. There is a square root kind of relationship available, but let us assume for a moment that we have a linear relationship. So basically what we are saying is that our capacitance C is equal to some initial capacitance C naught, nominal value of the capacitance, minus some constant K times M of t. Why did I put K? To match the unit, because this M of t is in volts and C naught is in farad. Therefore, what is the unit of this guy? Farad per volt. So therefore, this is the voltage across the capacitance of the reverse biased PN junction, and it oscillates or it varies around some fixed value of the capacitance. Okay, so let's say C naught is the nominal value of the capacitance without application of the applied voltage. Let's say M of t is equal to 0. Let's say you didn't apply the voltage, therefore let us take M of t is equal to 0. Therefore C is equal to C naught. And as you apply an external voltage, it varies in this manner, C naught minus K times M of t. Okay, so if this is the message signal M of t, and you apply M of t across the reverse biased junction, this will create a capacitance C naught, which has actually it will not be such a nice linear relation, but let us assume for the time being it is a linear relation. Actual relation may be a little more complicated, okay, and we will discuss that separately. Therefore, your frequency of oscillation omega naught is equal to, we said, 1 over root of LC. Now C is changing with respect to C naught minus K times M of t. Substitute in this relation, 1 over square root of L times C naught minus K times M of t. Okay, now you take C naught commonly outside, 1 over root of L times C naught of 1 minus K times M of t by C naught, like this. Now this I can rewrite as square root of L naught C naught, L C naught, then this becomes 1 minus K times M of t by C naught whole to the minus 1 by 2. Okay, so this expression, now again expand this using binomial series, then you will get square root of L C naught multiplied by 1 minus K times M of t divided by 2 times C naught. Okay, now this one let me call omega naught. Therefore omega is equal to omega naught times 1 minus K times M of t divided by 2 C naught. Okay, and this omega naught is the carrier frequency, nominal carrier frequency. So carrier frequency that you will get in the absence of modulating signal, that is when M of t is equal to 0, then your modulated signal will be the same as your carrier signal. Okay, because when M of t is 0, you left with only one term, omega naught. Okay, so now let me write down this relation, omega naught times 1, is it 1 minus or 1 plus? Because 1 minus, already in the power you have minus, this minus comes here, it becomes 1 plus, and we are neglecting the higher order terms in the Taylor series binomial series expansion. So omega is equal to omega naught times 1 minus K times M of t by 2 times C naught. Put a plus here. Here also put a plus. That's it. No, here it is minus only. Okay. Now let me rewrite this again. Omega naught times 1 plus Kf dash, if it is a frequency modulated signal, times M of t. Therefore omega times omega naught plus kf times m of t, where kf is equal to k suffix f omega naught then m of t. Now let me call these two guys as kf dash. Now here I put kf dash, here also dash, therefore kf is equal to kf dash times omega naught. Therefore this is omega is equal to omega naught plus kf times m of t. That's it. So note that even this condition kf times m of t is satisfied. Kf that you have here, this kf, the frequency modulator constant is quite large, and this will be quite large value. It's a frequency modulator constant, kf is. Okay, kf is also called proportionality constant. Proportionality constant. So you directly obtain fairly large modulation indices because you don't have restriction in kf. Okay, you can choose whichever you like, this kf, but you have a restriction in kf dash. This one you have some restrictions because omega naught is typically quite large, and this factor kf is sufficiently large for us to obtain wideband FM signal directly. So this is a principle of a direct FM generation. So the principle is really very simple. Now detailed design will depend on the design of the oscillator, and then you replace the capacitors in the oscillator with this reverse biased PN junction diode. Okay, so in this circuit what you do is, where is the circuit diagram? Yeah, this circuit you replace with a PN junction diode, reverse biased PN junction diode. Then your resonant frequency will depend on the amplitude of the message signal. Okay, therefore with this reverse biased capacitance in this location, capacitance, and you can generate the output frequency with respect to your amplitude of the message signal. Okay, so this will become your FM generator. Now what are the pros and cons of this what I call direct method? Okay, let's talk in terms of factors that we discussed earlier. Namely, we consider two factors which were important when we discussed the indirect method. One was frequency stability, the other was distortion. Okay, so in the direct method there was no distortion. Okay, if you have a perfect capacitance dependence like this, there is no distortion. We get a perfect FM signal in the direct method. Of course, for phase modulated signal, instead of working with m of t, you will work with a derivative of m of t. That will be the only difference. So you can use the circuit for both the FM signal and PM signal. However, as far as frequency stability is concerned, what can we say here in this direct method? Will it be as good? No, the answer is no, because we don't have a crystal oscillator in this circuit. Okay, the feedback circuit, that is the LC component, are not coming from the quartz crystals. They have to be separately realized because one of the component is the variable capacitance. In fact, the capacitance by its very name is variable, and therefore it is subject to drift and all the effects that are associated with the any passive component or active component is in this case like depends on this components. So all the drift effects will very much be present, and you cannot be shown that the omega naught that you are going to get will be constant for all time. It's very simple to show because there is a function of time. So the frequency stability is greatly affected in this case. Okay, so the carrier frequency is greatly affected because the carrier frequency also again depends on the capacitance C, greatly affected in the circuit. So even though you don't have frequency stability in the basic oscillator, it is possible to generate a complete system which has other components to make the overall system which has the frequency stability, but that becomes a very complicated system. Okay, I will not go into the details and how an FM generator can be made into a stable FM generator, but it can be done, but that becomes very expensive. Okay, so these are the pros and cons of the direct and indirect methods. Okay, let me comment some important points. Okay, some important points. Point number 1. Okay, it produced wideband FM. The direct method it produced wideband FM directly. Wideband FM directly, but this is not possible in indirect method. Why? Because it generates narrow band, and from narrow band to wideband you have to move on. And the second one is, however, it can be made to have the required frequency stability. So frequency stability can be stabilized. Okay, so therefore stabilization is possible through an appropriate feedback system, which makes it quite expensive because we don't have crystal oscillator in the circuit. So therefore the feedback circuit has LC component, and that LC component changes with respect to temperature and time. So if you have done some discussion on feedback, you must have also learnt that the feedback, particularly negative feedback, can be used to stabilize the system. So one can design a special negative feedback system, that a negative feedback system, that is control system or some kind, which ensures that even though there is a variation in the frequency due to drift, its effect can be minimized. Okay, so using a negative feedback system, one can easily control the frequency drift. Okay, so this is the direct method of FM generation. So in the last lecture we discussed indirect method of FM generation, and this lecture we discussed the direct method of FM generation. So with this, I think I have given you a reasonably a good idea of how FM signals can be generated. There is one more class of method based on relaxation oscillator that we will take up in the next lecture if time permits, or else you can study on your own from the textbook. Okay, now let me stop at this point. In the next lecture we will start. Let me stop at this point.